Okay, let's just dive right into this with a number that is, well, it's honestly staggering. 130 million. Just take a second to really wrap your head around that. That is the estimated number of space debris fragments orbiting our planet right now. We're talking about this massive swirling cloud of dead satellites, spent rocket stages, and just tiny little fragments of shattered metal zooming around Earth at tens of thousands of miles per hour.
And looking at a number like that, it begs this massive, almost impossible, logistical question. Who is going to clean up 130 million pieces of space debris? I mean, obviously, we can't just send a giant garbage truck up into low Earth orbit to scoop it all up, right? The sheer scale and speed of all this orbital shrapnel make it literally one of the greatest engineering challenges of our time. But what if the solution doesn't require a new invention at all?
Well, that brings us to the focus of today's explainer. There's a fascinating new study in Frontiers in Astronomy and Space Sciences that reveals this really incredible dynamic happening right above our heads. So let's look at the Sun, Earth's unexpected space sweeper, and find out exactly how solar activity acts as a massive, completely natural vacuum cleaner for our increasingly cluttered orbital environment.
Part 1. The Space Cleaner, our solar system star. To really get this, we're going to have to totally rethink how we view the center of our solar system.
Normally, we think of the sun as just a static, distant source of light and heat for Earth's surface. But in reality, it's a highly active participant in our orbital environment. See, low Earth orbit isn't some perfect, empty vacuum like you might imagine. It actually contains a very thin, residual atmosphere. And when the sun gets highly active, it actively heats up this gaseous layer surrounding our planet.
Moving on to Part 2, atmospheric braking, the physics at play. Think about driving a car down the highway on a really calm day. Now imagine suddenly hitting an incredibly thick, heavy headwind. What happens? Well, your car immediately experiences resistance and it slows down. This exact same fundamental principle applies in outer space, just, on a cosmic scale.
It all happens in this really elegant four-step cause and effect chain. First, solar activity rises and the sun gets restless. Then, for step 2, all that extra energy causes Earth's residual atmosphere to heat up and physically expand farther out into space. Step 3, because the atmosphere has expanded, it creates a much thicker headwind in low Earth orbit, which significantly increases orbital drag. And finally, step 4, all that space junk smashing into this thicker atmosphere loses its speed and falls much faster toward Earth to burn up.
But how do you actually prove an invisible, expanding gas is slowing down space junk? That brings us to Part 3, a 36-year investigation tracking orbital debris. The researchers here didn't just guess. They conducted some seriously rigorous, long-term detective work to confirm this mechanism.
So the really crucial point here is the contrast in scale. While there are 130 million fragments out there, scientists got hyper-specific to prove their theory. They isolated and tracked the meticulous trajectories of just 17 specific pieces of debris that were originally launched all the way back in the 1960s. And they followed these 17 fragments over a massive 36-year period. By observing them for that long, they were able to cover 3 complete 11-year solar cycles. Then, they took all of this trajectory data and cross-referenced it directly with historical solar activity records from the German Research Center for Geosciences. And all of that meticulous tracking revealed a major, totally unexpected plot twist. Part 4. Critical threshold. A sudden trigger point. The scientists discovered that the relationship between solar activity and orbital drag isn't just this slow, smooth, predictable slope. Actually, let's just read the exact words from the lead author of the study, Aisha Asharuf. She stated, "For the first time, we observed that beyond a certain level of solar activity, this loss of altitude occurs significantly faster." Guys, this is a huge revelation. They found that there is a specific, sudden trigger point. Once solar activity crosses a certain threshold, the atmospheric braking effect basically kicks into overdrive, pulling debris down out of orbit at a much more dramatic rate than we ever previously modeled.
Now, while this natural cleaning cycle sounds like absolutely amazing news for our cluttered skies, we do have to pivot to reality for a second. Part 5, Satellite Impacts, the Double-Edged Sword. Because unfortunately, physics doesn't differentiate between dead space junk and our vital, multi-million-dollar technology.
The reality of a highly active sun acts as a massive double-edged sword. On one hand, for space debris, this increased drag is fantastic. It provides a highly helpful,
totally natural cleanup of our orbit. But on the other hand, our active satellites are flying through that exact same thickened atmosphere. This forces them to constantly fight against the headwind, performing orbital corrections just to maintain their altitude. And doing that burns through precious onboard fuel way faster, which severely shortens the mission's lifespan, especially if that satellite happens to be launched near a period of maximum solar activity.
Which leaves us with a truly fascinating yet kind of precarious problem to solve. How will we balance our orbital ecosystem and manage satellite launches during future solar maximums? I mean, we desperately need the sun's activity to help clear out the millions of pieces of dangerous debris threatening low Earth orbit. Yet, that exact same natural cleaning mechanism acts as a direct threat to the lifespan and fuel reserves of the technology we rely on every single day. As we plan the next generation of space exploration, mastering this delicate dance with the sun's cycles isn't just going to be helpful, it's going to be absolutely essential.